All right, welcome to the second part of my lecture on Chapter 2. Okay, and I just wanted to give a quick example that recaps a lot of the rules that we discussed in the last lecture. Okay, so let's consider this example. So a disease affects 10% of a population, and let's name that disease A. And disease B affects 15% of the population. Five percent of the population has both disease. Okay, here's our very first question. What proportion of the population is affected by one of the diseases? So that is disease A or B. How prevalent is it? And if I was to answer this question, that's probability of A or B is equal to P of A plus P of B minus P of A intersect B. Okay, so we're told 10% has A, 15% has B, and 5% has both. So I think at the end of the day, that's 20%. Okay, so that was just a recap. The key there was using this general addition formula right here. Okay. But I can ask other questions as well. So, what proportion are affected by B only? And I can do this by doing a Venn diagram. Here's going to be A, that's 10%. Here's B, that has 15%. But remember, this intersection right here, that has 5%. If I want to obtain B only, it's going to be that area, excluding the intersection. And I can write this as probability of B only. That's going to be this 15%, which is the entire red circle, minus the blue proportion, which is 5%. So that's 10%. Okay. Here's a second question. If an individual has disease B, What are the odds they have disease A? So there's a keyword here, and that's that if. Other keywords are going to be when, given, or if. Okay. Those are common keywords for a conditional. Okay. So let's answer this question. It's asking us about the odds of A, so probability of A given B. So this is asking for probability of A and B divided by probability of B. A and B, 5% have both. The probability of B is going to be 15%. So this is a 1/3 chance that they have disease A if they have B. Okay. Let me give you another example here. Okay. And this will also be related to disease. Okay. So in a certain area, maybe it's a gym, maybe it's a grocery store. We're going to have 100 people are exposed to a virus or flu. Each individual has a 2% chance of catching the virus or flu, whichever you prefer it to be. Okay. The question is going to be this. Now, I'm going to ask you to assume each individual's odds are independent. Okay. Here's going to be the question. What are the odds at least one person catches the flu or the virus? Okay. So let's answer this question. Probability at least one catches it. I'm going to use the complement rule. And the complement of at least one is that no one is the virus. Well, if no one catches the virus, that means that the first person does not catch it, and the second person does not catch it. And that continues all the way down to the 100th person does not catch it. Because I asked you to assume independence, that means that I can multiply. Okay, and now I'll need a new note. Okay. 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 Well, the probability of not catching it. Well, that's the probability of not catching a virus. That is going to be equal to 98%. And how I got that 98%, that's going to be 1 minus the probability of catching the virus. And we're told in the problem, the probability of catching the virus is 2%. Okay, so we need that side fact. Okay. Now going back to the calculation, probability, no one catches the virus. The probability at least one catches the virus. That's going to be 1 minus the probability at least one. Probability none catch it. And by the multiplication rule, this is going to be 1 minus 0.98 times 0.98 times 0.98. And because there are 100 individuals, this will be minus 0.98 to the 100th power. Now, we just need to do that calculation. And when we calculate that number, we're going to get this. That's going to be 86.7%. So that's an 86.7% chance that at least one person catches the virus, just based on that calculation. So I just wanted to emphasize some key things that we used in this problem were independence to multiply and the complement rule. Okay, now let me give you one last example. So, in a certain population, 98% of individuals do not have a virus. Okay. And of those without the virus, there's a test to see if the individuals have the virus, and the test is 99% accurate for these individuals. Okay. A test confirms this 98% of the time. Excuse me, not 98%, but 99%. So that is, if you don't have this virus or disease, this test will confirm that you don't have the virus 99% of the time. Okay. If you do have the virus, the test will confirm this 95% of the time. So that there's some keywords here that I'd like to point out. So one of them being this if. If you do have the virus, so that's conditional on you having the virus. The test will confirm that you do indeed have the virus 95% of the time. Okay, then it says here of the individuals. So if you are an individual without the virus, so this of the individuals is a conditional. So is this if. Okay, and then I like to draw a tree diagram. So this is going to be V for virus. Only 2% of the population lives there. This is going to be NV for not virus. 98% of the population doesn't have the virus. Then there's going to be a test. And I'm going to redraw this tree diagram on the next page. So for each branch, there's a test, and you can test positive or you can test negative. Positive or negative. So let me redraw this tree. So not virus, that's 98% of the population. Here's going to be the virus, that's 2% of the population are affected by the virus. Now, this applies to our population. Then there's a test. There's two outcomes for a test. You can test positive, you can test negative. This instance, this is called a false negative, meaning that you did have the virus, but your test said you do not. That happens 5% of the time. This happens 95%. Now for the non-virus population, it can test positive, that's rare, or it can test negative, which is more common. It's accurate. It accurately describes that 99% of individuals do not have the virus. But sometimes it makes a mistake. Sometimes it says you do have the virus. It says there's a positive, that you're positive, when in fact you do not have the virus. That happens 1% of the time. That's called a false positive. And feel free to research this. These are things that are medical terminology and that actually occur. So here's going to be my first question. What proportion of the population tests positive and has the virus? Well, that's basically asking what is the proportion of true positives. So probability of virus and positive. Well, I'm just going to use this conditional probability to calculate this. It's going to be probability of virus times probability of positive given, which is that bar, virus. And that's going to be this 0.02 times 0.95. So in other words, it's just this path right here. The path to the positive, the true positive. And if you were to calculate what that number is, it's going to be 1.9%. Okay. Now, you'll want to have this tree diagram in mind when I do the rest of these problems, okay? Okay. You can also ask this question. What is the probability someone from either population, just a randomly chosen individual in the population, they don't have to be in the virus or the non-virus category. What is the probability of a positive test? And if we were to answer this, probability of positive, probability of positive can happen in two ways. You can have the virus and be positive, or you cannot have the virus and be positive. Now, because of that or, they are indeed disjoint. You cannot have the virus and not have the virus at the same time. So I will simply add them, virus and positive, plus probability of not virus and positive. We calculated this number last time. That is the 1.9%. Plus probability of not virus. This is going to be the general multiplication rule. So that's going to be probability of not virus times probability of positive given not virus. So if we go back to the previous note, okay, we first took this path right here, right? That represented the probability of virus and positive. This path represents the probability of not virus and positive. So we're adding those two multiplications together. Okay. So this is going to be 1.9% plus probability of not virus, that's 98% of the population, times positive given not virus, well, only 1% of that population, of the not virus population, test positive. And that final number is going to be 0.0288. Or 2.8%. Now, finally, I have one last question for you. And the question is this. This is an if the test is positive. What is the probability the individual in fact has the virus? Now, there should be a keyword that's going off in your head right now, and that's this if. So that if is asking us to calculate something very specific. It's a conditional. So it's asking us to calculate probability of virus given positive test. Okay. And because this is a given with that keyword right here, there's a very specific way to calculate this. This is the probability of virus and positive divided by probability of positive. We calculate probability of virus and positive. That's that 1.9%. So 1.9% is 0.019 divided by the probability just anyone in the population tests positive. That would be 2.8%, 0.028. Okay, and technically there's another 8. When we compute that fraction, we're going to get that this is 66%. So there's only a 66% chance that you have the virus if the test indicates you are a positive. That's very interesting. Now here's another thing to consider. Often in real life with these false positive and negatives, people ask them to come back and do a second test or to do a blood test to confirm that they do indeed have it. That's very common with HIV or any sort of STD. So oftentimes people will do a second test. The other thing that I like to mention is look at the probabilities of the test getting it right for the specific populations. They're very good, but even though they're very good, like 99% accurate and 95%, we're still only at 66%, and that's quite astounding. Okay, well, that's all that I have for this lecture. That concludes chapter 2. I'll also say this last example that we did is an example of what's called Bayes' theorem. I don't explicitly ever write down Bayes' theorem because it can be answered just using a simple calculation of a conditional probability. Bayes' theorem is conditional probability. And rather than just overwhelm you with probabilities, rules of probability, I just would like you to be able to calculate conditional probabilities. They're very important and probably the hardest for students to deal with. Okay. Well, thank you again. Next time we'll tackle chapter 3.